Okay, so let's look at the second term, okay? So the second term is here. Now the thing is that one thing we assume is that our wave packet, the initial wave packet was very, it was quite sharply defined in momentum space, okay? So it means that, the initial wave packet was was sharply peaked. So that, what does that mean? That means that just 1 second, yeah. Yeah, right. So we assume that the initial wave packet was very sharply peaked around K0, right? So that means that, now this guy, this coefficient is actually dependent on K1, right? Because B is dependent on K1. But this whole thing is being multiplied by A of K1, which is a Gaussian, right? And A of K1 is very sharply peaked around K0. So when we are doing this integral in the range where this integral is being done, we can roughly think of this as being a constant. Its value being taken as the value at K1 equals to K0. So for the second term, we can assume, we can take B over A to be B over A at K1 equal to K0, since we assumed that A of K1 is very sharply peaked around K0. Now, if you don't want to do it, if you want to say, no, I don't want to make this approximation, you're welcome to do that, but you might have to do a numerical integration, okay? But what we're interested here is to get some sort of physical intuition out of, what is happening. And so, this is something we can do. Okay, any questions about this? So if I do this, then what happens from the second term is that I can take, this guy and this guy out of the integration. And what we have left over is just, a normal Gaussian integral, okay? Okay, so what do we have left over? So, so we can take out B over A and theta minus x out of the integral, and we get, as a result, this integral. H bar K1 squared T over 2m e to the power minus K1 minus K0 squared del squared over 2 e to the power minus I K1 x minus a d of K1, okay? So now we can do this integral easily by, essentially if you do this, this guy is going to give you psi of r. And if you do this, then you basically get theta of minus of x, a Gaussian of this form times b over a at k0. So what is this Gaussian? This is a Gaussian centered. So this is a Gaussian centered around x equals to a minus h bar k0t over m. And when t becomes large, we can just ignore this. So as t becomes large, the center of the Gaussian becomes approximately minus h bar k0t over m. Okay? So this is the reflected Gaussian. So from here, you can say, okay, I can just calculate the psi reflected, the reflection coefficient, and this just becomes b over a evaluated at k equals to k naught, okay, which is given by square root of e naught e minus e minus, okay, so this is e naught. Let me define e naught. E naught by v naught by 2 e naught square root. So, okay, okay, let me just also use square root here. Plus square root of e naught plus v naught. The whole thing squared, okay? Where e naught is h bar squared, k naught squared divided by 2m. So this gives the reflection coefficient. Now, doing the same thing and working out psi t, you can work out, psi t is the last term, and you can work out the transmission coefficient, but there's an easier way. And you know that r plus t is 1, so you can just subtract r from 1, and then you get t, and then t just becomes, it's 1 minus r, it's c over a, at evaluated at k naught, e naught minus v naught square root divided by square root of e naught, okay? So now note that e naught is greater than v naught, okay? And because otherwise you would not get a transmission coefficient, right? So so this is basically oh, sorry, I just want to note that. Yeah. So this is non-classical behavior, right? Because in classical mechanics, if you had the energy of the incident particle greater than V naught, then all the particles would be transmitted, right? Their kinetic energy would be lessened, but they would be transmitted. But we are seeing that in quantum mechanics, because of its wave nature, some of the particles will get reflected. Okay, so I think, yeah, this is it. I think I'm going to spend a few more minutes to show how the Gaussian integral is done, but do we have any questions so far?
I have a question. So is that because some of the particles will probabilistically have less energy than V naught?
No. No, that's not true. This has to do yeah, that's a very good question. That's not the case, because one thing you can do is the following. So here, we took a distribution of different, you know, energies of particles, right? And you're saying, okay, there are some energies of particles because the wave function, there is a probability that some of the particles will have less than, the energy of V naught, right? That's what you're saying.
Yeah.
But if you instead do this, if you say, okay, instead of, I'm just going to have a monochromatic, plane wave coming in, okay? So it's not a Gaussian, it's not a wave packet, but a monochromatic, an infinite plane wave, right? So which has a very definite, a very definite, incident energy, right? So if you do that, then you would not expect classically any particle to be reflected, right? Because if the incident energy is greater than the potential energy barrier, then all the particles will be transmitted, right?
Yeah.
Right. But you find in that case that you still get this expression for T naught, for T. So even in that case, there is a reflection that some particles will get reflected. Okay, so this has to do with the wave nature. So the fact is that, when we are solving the Schrodinger equation, we are completely oblivious to the fact that there are any particles involved, right? We are solving a wave equation with a certain kind of, boundary condition. It's only after the fact that we have solved it that we take the square of the modulus of the wave functions to interpret them as, particles, or the number of particles, right? So that's really what tells us that there is going to be particles which are going to be reflected. It's not that it is actually, it's not that it's actually that some of the particles are probabilistically have less energy. Okay?
I see. I think it makes sense.
Yeah. So